Well, hello everyone. I hope everyone's having a good day. Let me go ahead and open us up in prayer, and I'll give you a sense of the things that we're going to be covering. So, dear Heavenly Father, Lord, thank you for the chance to be working with each of the students in the course. I pray that the material will be clear. Pray it can be an enjoyable experience of getting familiar with computer architecture and organization, and that this is going to help each student to get the job of their choice or opening the business of their choice as they're navigating towards their future. Lord, I also pray that you would help them in their spiritual formation, Lord, that all the times that they've been able to study scripture, the various courses, the chapels, that they've been able to study scripture, you help them to take that to heart. And Lord, give them the understanding to how to see how to drive theological concepts and guidelines, how that they can be guiding their life in the future. And finally, give them interesting and creative ways for faith integration. In Jesus' precious name, we pray. Amen. Okay, well, what we're going to cover today is I have this second lecture that's on the instruction set and assembly language. And so this is the one that's most closely related to our Mars MIPS um, assembly language project work that you're doing. And I'm starting to see the inputs that people are producing. And so it sounds like it's been an enjoyable experience. You guys are getting your hands around this. And so I'll spend a little bit of time going, probably for the last time, going through our Mars MIPS emulator, talking about some sample projects. And then when I want to transition to be thinking more about our Arduino kits. And so I'm going to spend a little bit more time with the charts I showed last week, and also kind of go a little bit further with that to try and give some context about that. So let's go ahead and we're going to be focusing on instruction sets here, but let's just reflect on what we saw in the last lecture since they're related. And so in chapter 13, we talked about the characteristics and functions of instruction sets. And so we typically go thinking about the Intel 86 and the ARM as two general classifications of architectures. And so we talked about the various elements of an instruction, how many addresses. So we're going to have 2 or 3 registers. What are the things that we're going to be putting in the operands? Numbers, characteristics, logical data. Those are some things that we got a chance to be seeing there. Now for this lecture, what we're going to be doing is, well, let's think about the instruction format, the length. I'm focusing on things that what might conceptually be more straightforward for you to get your heads around. And then I'm going to be talking about addressing modes. And there's going to be one summary chart that I think is going to be really helpful. And so I want to spend the bulk of the time talking about that, as well as talking about the instruction formats, because we're going to be then trying to correlate that to a certain degree with what we're seeing in our Mars MIPS emulator. And maybe this will help you understand what's being passed to the CPU. Remember the main component in terms of computational abilities. Well, let me just ask this a question. Does anyone recall what is the main computational engine in the CPU? What's it called? You can put it in the chat or just go off mute if you like. Anybody have a recollection of what that is? Thumbs up if you have some idea. Maybe you're having a tough time coming up with the words, or if you're not, I just want to get a sense where people are at thinking about this. So thumbs up or thumbs down. It just helps me to see where you're seeing this. Okay. So getting ups and downs, so that's fine. So just to give a reminder that I'm hoping that some of these terms will sink in, I'll put it into the chat so you can see that the arithmetic logic unit. Okay, and so that's the thing that all of this control and the things that we're trying to have it do are coded in the opcode. Okay, well, let's get into this. And so here are the various types of addressing modes, immediate, direct, indirect, register, indirect, displacement, and stack. So let's just make a couple of comments here. And so I think most of you have taken CS 260, talking about data structures. And so this term of stack may be familiar to you. And so I want you to be thinking about that, because we're seeing this here in a very simplistic way. You can just depend on the stack rather than depending on multiple registers. So folks, remember, in terms of a von Neumann architecture, a CPU, I/O, and memory, where do we find these registers? Anybody remember which one of those three it shows up? You can type it in the chat if you'd like. Anybody want to venture a guess on that? Do you guys have a recollection of having me mentioning the von Neumann architecture? Is that something you guys remember me mentioning? Okay.
Sorry, were you saying?
And so do you guys remember how many components are in the von Neumann architecture?
Was it like 3?
Yeah, there's three components, the CPU, the memory, and the input and output. Okay, the registers are in the CPU. And so that's the thing that I wanted to have you have a recollection of. And so this is that list, but now we have an illustration. And so this idea of immediate, and so like this would be a value of, say, like we would have like 10. So like we do a syscall, and we're going to see this when we get into the Mars MIPS emulator, some of the various kinds of command. This would be like, that would be what would be contained in this field. Well, that's one way of doing commanding. So we have the another one here where we have a direct. And so what we're doing here is there's information that is in the instruction. So here, anybody have a guess what this front is that's grayed out here, what that might mean? You guys remember the general format of what a command is? Let me see if I can go back and show you what I mean. Okay, so here is the opcode, and then we have things that we're going to be processing with that opcode, and that's what I'm just trying to have you guys remember when I'm showing you that. Try and get out of this mode. Okay, I'll just have to manually go back. So okay, so this is trying to show you what an instruction looks like, but we're trying to be putting it in bit format. And so here we have an immediate, and so we have like a value like that. Here we can be showing a direct, and so a value here is pointing to a location in memory. Okay, so this is memory. Then we can have indirect, and so that location that is in here is pointing to a place in memory that then shows you the value that's supposed to go into that. So I think I mentioned this before. How many people have experience programming in C or C++? Why don't you just give a thumbs up So a few of you, um, so this is, if you've had some programming like this idea of indirect addressing is what we're talking about here. So here we're saying, okay, I want to go to 101 Main Street. And so you just go there. And this is saying, okay, I want you to go to this other location, and that other location is going to tell you where you want to go. So there's two steps that need to be taken when you're going indirect. So you can see this is going to be more involved than direct. Here we have a register. So this is different than memory. Memory is over here, then we have registers over here. And we're saying like $ T0 or something like that. So this is what we're doing when we're having that we're going directly in registers. Then we have this idea of indirect. So we have this here when we're doing it in memory. Well, now we can be saying, okay, we're going to be pointing to a register, and a register is going to give the value. We're in memory where we're going to be putting things in. So all of these situations, the goal is to get the operand into the command. And so you can see that sometimes it takes a little bit more of an involved process to get there. So that's register indirect. And then finally, displacement. Now we have a register. Then we need to add that register, the contents of that register with another value. And that together forms where the location in memory where that operand is. So this is like a combination of indirect and registers showing you with that. And finally, we have the stack. And so thus there is no registers or no operands that are shown in the command. It's just literally what is the control? Is it going to do an add or whatever? And the information that's going to be utilizing it is going to be on the top of the stack, on the register stack. Does that make sense? You guys tracking that? Just give me a thumbs up if you're tracking what I'm trying to give you a sense of what's going on there.
Professor, when you mean like stack, that means like kind of like a list of orders it's gonna do. Like it does it from the top and then goes all the way down to the bottom.
Yeah, so let's just review for a minute what a stack is. And so a stack, and so it's like a stack of books. And so so if I add a stack to this book, I'm going to add it to the top. So let's pretend this is a thick one. So it's like that. And so this is the one that I'm going to be able to get access to first. If I want to get to access to this next one, I have to take this one off the stack, and then I can get to that one. And so that's what we're seeing here. So I can have things that are piled up into the stack, and thus it has to be in a certain order for us to do computations. And this was a topic that we got a chance to get some exposure to in CS 216. So I just wanted to maybe have you be mindful of that. Does that help, Nathan? Does that help other folks? You guys catching this?
Yeah, thank you.
This gives a response from other folks. Are you guys catching what I'm referring to by a stack? Okay, getting some responses that you're seeing with what this happens. So ultimately, this is what we're shooting for. This is whatever kind of command we want to be doing: add, subtract, store, load. And this is the value that's trying to help us to do that. So if we're going to do add, and say we have 3 registers, it would be add register 1 with register 2 and put the results in register 3. So we're just trying to show you how we would get that operand, that value, in these various different ways. So is this making more sense to you guys? Are you understanding these 7 different addressing modes? let me see if, for those that may still be trying to get your head around this, is there anything that would be helpful for me to explain a little bit further? Or if you want to just think about it a little bit, just give me some feedback so I have an idea. Okay, well, I'm going to press forward, but I think this is a useful chart to give you a sense of how all of this works. And so there's some pros and cons for each of these. So immediate, there's no memory reference, but then we have limited operand magnitude. So it's an integer, and so we can't have like 2 times 10 to the 11th or something like that for that. Direct, it can be very simple, but once again, there's a limited address space. So we're seeing those options here that are listed. Indirect, we can have a larger address space and we can have multiple memory references. Those are things that we can start to see there. Register, this is going to be really fast. And so if we have loaded this into the registers, that's going to make it, that's going to be a benefit, but you have to load things into the registers. We want to keep that in mind. Registers indirect, it's a large address space, but it takes extra memory references. Displacement, this is going to be really flexible, but there's going to be complexity that's going to be part of that. And so we can see that of all of them, this looks fairly complicated to be viewing. And finally, for a stack, not everything can just be putting into this nice type of way of how we need to be accessing the data. And so that would be something that would want to be thought about when you're thinking about that address mode. So then we have some more details of that. And since we have this chart and we have this summary table, I'm not going to be going through these in as much detail, but just wanted to give you a sense that you can go ahead and go to Stalling and read up on this a little bit more. So we have the immediate addressing. So conceptually, pretty simple. We're going to be seeing that. We have indirect addressing. And so the reference to the address of a word in memory, which contains a full length address of the operand that we see when we're using that. We have register indirect addressing. It's analogous to indirect addressing. The only difference is whether the address field refers to a memory location or a register. So this is, once again, we're focusing on a register rather than memory. We have that in our summary chart that we were showing. So we can have indirect here, or we can have register indirect. And so registered indirect, there's 2 steps here. If we're just doing a indirect with memory, we're not using a register, so we're going to have 2 memory engagements here. So you can be seeing that memory is going to be slower than register, so this is going to take longer. This is going to be a little bit faster comparing those 2. So you can be thinking about that. Displacement addressing, this can give a fair amount of complexity, and this would be the kind of thing that you could be doing in C++. Say you're trying to load information to your monitor, and there's a huge chunk of things that you have to get displayed onto that monitor, an image or something like this. This may be an example of something where that could be of use. And then we have relative addressing. That's something that you can be using. We have that available. And here's just some more things: base register addressing. And so ultimately, indexing is going to be a helpful thing when we get into some of these more complicated modes of how we're going to be computing where we're going to be needing to go, as we're seeing in this figure here with displacement. So I think that's, and then we just had finally, we can just be using the stack. So maybe you have an architecture that's so simple that you don't even have any registers that you load in the way that we've been speaking to, but you have a stack. And so that's going to take a little bit more time and energy to be doing code, but it still would be possible for you to do that. Okay, I'm going to skip over some stuff here. So let's think in terms of how things are done between an x86 architecture and an ARM architecture. I'm not going to dwell in this in much detail here, but this is a legacy system, a PDP-11. And you can see that this had a total of 12 bits. So this would be a memory reference instruction. Here is an input-output instruction, a register reference instruction, and these are all 12 bits. Interesting, but that was a time where 12 bits was adequate. Here was a PDP-10, still not an even increment of 2 to the something, so they have 36 bits. But you can see this is starting to look a little bit more like the format that we see in modern computers. Now we have this idea, well, what about having a variable length instruction? This is the thing that the x86 architecture has leaned heavily into that. And so here is the first of 2 charts that give us this general sense. This still isn't talking about an x86 architecture, but you can see that here we can have different lengths of commands. And so the PDP thought about that as well. We have VAX, and here is finally the one that I'm going to focus on, but just was basically alluding to there are some legacy types of computer architectures, but the x86 and the ARM are the ones that we're focused on in this course. So here is the general command, and look at this. It could be 0, 1, 2, 3, or 4 bytes. This can be an opcode, 1, 2, or 3 bytes. Here we have some other information here. We have this idea of displacement and immediate. And so each one of these can be 0, 1, 2, 3, or 4 bytes. And for these other things here, we can see that there's more details that are contained as part of this general format. So that's a lot of information that we're getting a chance to be exposed to. I'm still trying to keep it at a higher level, but if you want to dig into, those are the kind of things that are there. So x86, they're variable length instructions. And so this is what's called the complex instruction set computing, CISC. And then for the ARM, it has a fixed length. And so everything is 32 bits. And so here we can be seeing the different kind of modes that are possible. This is showing data processing immediate shift, data processing registered shift, data processing immediate, load store immediate offset, load store register offset, load store multiple, branch, and branch with link. And so these just give you some examples of the types of instructions that are allowable and what each of these 32-bit part of this command are trying to refer to. So just to focus a few minutes on these 2 charts and see if you're getting a sense of what's going on here. So variable length for x86, fixed length for ARM instructions. That's a takeaway there. And so that means that you only have 32 bits. And so once you're out of it, then you're out of luck. Versus with an x86 instruction format, you can, these are expandable depending on what exactly that you would like to be doing. A couple of weeks ago, I showed a quick summary of the x86 instruction set, and it's like huge as compared to an ARM instruction set. And so this is just where it starts to fold out when you look at those specific bits. So those are two charts that I wanted to be pointing out. So just to review, we have this one chart that talks about addressing. And so we are seeing this a little bit in our Mars MIPS emulator, like load immediate. So that would mean like this, load immediate 10. This would be the thing that we're putting into a register, and then we do a syscall, and that's actually going to tell the CPU what it is meant that you're trying to accomplish. Then I was focusing on two charts here to be reiterating the fact that the x86 instruction format is fairly complicated, and we can see that laid out here. I would refer you to Stalling for more details about that. And then as an alternative, a different type of architecture is having everything be the same length. And so that's what we're seeing with this chart. Any comments or questions on that?
So you said, oh, sorry.
This is what we're doing with our Mars ZIP emulator. We're using an ARM category of instructions. The MIPS is a example of the ARM architecture. Go ahead, Nathan.
Oh, I was gonna say, so you said that the ARM has like, I guess like a limited amount of bits it can use, but with the x86, there's like I guess like it could stretch out,
Yeah,
depending on like what kind of register you use or address register you use, something like that.
yeah. And so you can be having like tens, 20, hundreds of variants of like doing an add, for example, double precision, single precision, or add with just integers, add immediate, just to give you some ideas of the things that are available. That kind of flexibility is not something that we see in the ARM architecture. So thus you would have to be doing coding at the assembly language level different. Does that make sense?
Yeah.
So you might end up for one command that you would be doing in x86 architecture. You might take several commands to be doing it in an ARM architecture. That's just to give you a perspective. Okay.
Okay, thank you.
So those are the main points I wanted to drive home here. There's something in the ARM architecture, there's a shorthand where you have something called a thumb. And so instead of 32 bits, it's only 16 bits. And so you can be having instructions like this, but eventually it needs to be expanded into a 32-bit, depending on what you're trying to accomplish. Now let me just pause here. Here is a 16-bit way of doing an add. And so here we can have, we're pointing out the fact that we're going to be adding something to a register and then putting it back into the register. So we're adding immediate a value, putting it into R3 plus immediate 19, and we're going to be putting that result into R13. In a shorthand version, we can be just stating it like this because these are, you could argue, are redundant. So that's just a shorthand way that you can be doing things with the ARM instruction set. So those are the highlights that I wanted to share here. So here we have a variety of different addressing modes. And we're bumping into some of these as we go. But for your assembly language programming, you may or may not be encountering all of these, but we'll get a chance to see some of those in action. So we have the addressing modes. There's a difference. Some subtle differences between the x86 and the ARM, but the things that I was focusing on is the format difference between the x86, which is variable size, and the ARM instruction format that is always 32 bits. Unless we get into the 64-bit architecture, which we will get a chance to just hear about that some and some of the material that Stalling covers. Any comments on that? You guys following with what I have there? Just give a thumbs up if you're tracking with this or if you want me to go over something in more detail. Okay, I'm getting some feedback that you're tracking. I'm trying to keep it at a high level, so because I know there's a lot of information here. All right, well, let's go to our Mars MIPS emulator and just going to be pointing something out. And so this is a sample program. This is one that I've shown already where I'll just run it just to give you a recollection of what it is. And then I'm going to be showing you some other programs. So enter A, so we're going to add some numbers, 5, enter B, 6, and we get a result. So here we can see a load immediate. So this shows you one of these address modes that I was just referring to. And I'll just pull up that one slide so that maybe this will sink in. So this is what we're doing here. We don't have a very complicated type of activity. This is the kind of information that what this is we're going to be printing a string to the console. So here is the message we're going to be printing out. And this is, we're loading it into a register that the CPU is looking for, that it says, okay, if I have a syscall, and this is let me pull up. The syscall, so I have a syscall 4. That means it's going to print a string to the console. And so that's what we see that's being done here. So you see this is a load immediate. You guys, we've seen that a few times now. That just gives you an idea of that. You guys tracking what we're doing there? Does that make sense? So this is showing an example of this load immediate. We're just loading this value. And what is done in the Mars MIPS emulator, we're loading it into a specific register V0. So V0 is right there, and it has that value 10. You can see, okay? Make sense?
Sorry, Professor. So basically we're like loading the LI just means like we're loading immediately like the register and then like
Yeah, you're loading 4 into this register. That's what we do. Here we're going to have another load immediate 5. Load immediate 5. And then the very last one is this load immediate 10. And so that's what we're seeing in this V0 register because we ran the whole program. Make sense?
Well, basically, it's kind of like we want like these registers to load now, which is like basically like the what do you call it? Um, we want it to load. Uh, I'm forgetting the word for it. Um,
Load immediate or
yeah, I'm trying to figure out like so it wants so the load immediate just means like it wants the register to load like its function, I guess, like immediately. Like it wants it to do it what we want it to do. So like being able to print out like a print string or
yeah.
loading in a print string and then being able to read it.
Yeah, so load immediate, so LI, and then we have a value. So like 4 or 5 or 10, as we see in this program, is what's being spelled out here. This has so that's the value we're going to be putting into that register V0. And so we execute that command, that's what's going to happen. Then the next thing is this LA command. And so this is going to have the information in another register A0. A0 is here. And so let's look at that for a minute. So we'd have to be looking at the compiled version. And so this is where in this hexadecimal format is a little bit harder for us to be tracking. And we can see the order of how things are, like enter A colon. And so it's not in the order that we're used to seeing that we would like to have. It's flipped, and and so there's a couple ways where you kind of have to be following in the ASCII format to have us remember what's going on there. But you can see that enter A, and then we have enter B. And so those are things that are spelled out there for in the memory. And so we see all of those messages are down here. Okay. Well, some of you have already submitted your programs, and so here are a couple ones that are a little bit more complicated. And so here is a program to produce a sum of integers. And so I'm just going to compile that. And I'll go ahead and run that just to give you an idea. So enter an input value for how many integers do we want to sum. Anyone want to give me a number? You can put it in the chat if you'd like. Okay, 21. And so it produces the number for that. The sum of those is 231. So it's a little bit easier to look at the code here. So here is a so what it does is it starts with the largest value, and then it goes down. So for us, it would go 21 plus 20 plus 19, and so we're seeing that laid out here. So this is the how we do this, and so we have a loop. So we branch if not equal, and so we keep coming back to this loop here, and so we're going to execute these commands until we get all the way down. We branch to loop if the value of register V0 is not equal to 0. So once it's equal to 0, then it's not going to go back there, and it's going to go down here. So this is an example of a looping. Some of the folks with the discussion we've had about your project and what would be relevant for your overall project theme, this might be something that would be helpful for you to think about doing. So we've seen this kind of construct before, printing something out to the console, reading what's been typed in. We have that. Then we branch to the end if the value of V0 is less than or equal to 0. Well, we just put in that value, loaded it with the input number, so it's not. And then we just run through these elements, going from the largest integer and then cycling down. Okay, so let me just make another point or two. So this is the opcode, putting it in binary, all of this information that we have here. So let's think about this. And so anybody remember anybody remember what hexadecimal is? Does that just do a thumbs up if you remember what hexadecimal stands for? Okay. So hexadecimal is 4 binary bits together, right? Does that make sense? So we have 8 hexadecimal digits here. So how many bits would that equate to? Anybody want to venture a guess? If each one represents 4 bits, and so 4 times 8, anybody want to give me what's that value? Yep. So thus when we, and this other chart that I was dwelling on for today was this. So everything has to be put into 32 bits. Okay, so this very first one is load immediate 4. Load immediate 4. It's a little bit hard to read, but you can see this value here. These are the digits for that load immediate that are made available to be loading an integer. So that very first command is what we see that is laid out here. The only other item of complexity here is we're specifying what register we're going to be loading it to. So we're loading 4 into V0. Okay. So that's another program that has a loop. We're doing add, we're adding down. And so just do a thumbs up if you're tracking what I've got there. Is that making sense? Okay. Well, then I'll just do one more program. And I think anybody ever heard of the Fibonacci sequence? In one way, it doesn't matter what it is. It's just a sequence. Every new digit is based on previous digits. And so here is how you could be doing that in assembly language. And so I'll just go ahead and run this just to give you an idea. So anybody want to give me a number? Give me an integer, and we'll see what the Fibonacci sequence would be for that. 7, okay. Okay, give me a second. I think I may have too many things that are running here. I'm going to close out of this and then reopen it and open the Fibonacci just to see what's going on there. Give me a second. Okay, yeah, I've forgotten about this. Let me try and run it one more time. Okay, my mistake. I thought this was it you enter in a value, it actually computes one. So this does it computes the Fibonacci sequence, the first 14 digits. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So what I would have to do is I'd have to change this to another value, say 15 or 7, which was what we were was recommended here to do that. So for some of you, instead of doing an input and output, this might be an easier way of doing it, where you literally hard code what the value is going to be. And so you can think about that as a possible way of doing it. So we have add immediate here. We have add D. Let's look up what add D is. Add D is a floating point absolute value double precision. So double precision would maybe be the operative thing that we're trying to make this as long as possible, because you can see that these numbers quickly get large. And so having this double precision is what we're utilizing here, so we don't get an error. So say if I put this number too high, that's going to be an issue. So I think fibs is that's the array. So and then we have the size, and so if I wanted to make this larger, say 15, I'd have to change this to 15 and change that to 15, so there'd be two places. So you can set up an array, if you will. They're calling it an array. So it's a set of memory locations that we're utilizing to come up with the Fibonacci sequence. And so the Fibonacci sequence is related to two previous inputs. So here it's say item n, and n plus 1 is the next value that you have in that sequence. And so that's shorthand information for thinking about that. I think one or more of you may have looked at the Fibonacci sequence for one of your programs, and so maybe that's a little bit of a reminder of that. Okay. Go ahead and do a thumbs up if you're tracking with what I'm saying there. Let me know. Okay, good. So this may be more complicated than you'd want to do for one of your programs, but at least it gives you an idea of what's going on there. So I'm just going to transition now to thinking about our Arduino kit. And so I've already shown you this presentation before, but what I wanted to do was have us start to be thinking about the Arduino IDE, how we're going to be load things in and bring it more into focus with this IDE and a sample program. So I'll just snap through a few charts here. So just give me a thumbs up. Everybody have your Arduino kit. If you don't, please reach out to me. I can help you make sure that you get it. So I have a link that's in Canvas. And what I'd recommend is you start bringing it on Tuesday. We could start to play with it a little bit together. And we can also do some of that on Thursdays as well. It might be useful to turn on your webcam if you're trying to show your setup. So you have the basic Arduino kit. You're going to be putting in wires between these and the components that you would have on a wiring board. And so this just gives you an idea. The kits that you have probably are going to be about half of this size, maybe even a quarter of that size. But those are some possible things that you would have. And so it's a wiring board or solderless plug-in breadboard is what it represents. And there's a couple different ways of how you can be looking at it. For the engineers, this is probably helpful for you to, and you're having where these wires are connected. This is the schematic way of representing what a resistor is. And so just think of like a water faucet. If you have a resistor, it's going to start to make the flow of electrons. For a water faucet would be water. Then you have a diode here. And so with that arrow, it's going to allow current to flow this way, but not in the opposite direction. And so when you have these little arrows next to it, that means it's a light emitting diode, and it's a red, green, blue RGB LED schematic is what that represents. This is, especially if you're not familiar with how you do things, this is literally how you're going to be connecting it on your board. And so you only need a handful of wires that are connected. So this is the hardware part of it. And then we have the Arduino kit. And this is what it looks like. And so I'll mention the two parts here in just a second. And basically what you're doing in this program is you're having the three inputs, the red, the green, and the blue, that you're causing electrons to flow at a increasing or decreasing rate for each one of these things. And they're out of sync with one another, and you're going to see this RGB LED change color. And so I'll show a movie of that playing just in just a few minutes. So this is what it would look like. We have to be defining what pins are going to connect. So blue is 3, green is 5, red is 6, so 3, 5, and 6. So you can see 3 is here, 5 and 6, and so those are being hooked up there. And then we go into the ground on the other end. And so thus, with these resistors, we're going to be putting electrons going on each of these 3 inputs. And then it's going to then connect to ground as we see in this figure here. So we have those 3 pins that go to each one of those inputs. And then the 4th wire on the RGB LED goes back to the Arduino kit. So it's a one-way flow of information. You're coding it, you play the program, and you're going to see it transition from color to color with this. And so thus we have the code here. Here is a little bit more readable version of that. And so here we see those 3 pins that we're programming. And so there's 2 parts. We have the inputs. The setup is the way that they call it here, and the lower part is the actual what you're doing with your Arduino kit. So here we see fading time between colors. Fading out red brings green full. Fading out green brings full blue, brings blue full, and fading out blue brings in red full. So these are just a thing how we go from different colors. So this was a view of the setup that I had, and then I actually, the video is actually in one of the Canvas pages that I have, but this isn't very long, so I'll just show this. And so just, if you just see the LED here, you can see how it's transitioning from color to color. And one of our cats wanted to be a movie star, so she's starring in the background. So if you like cats, maybe you'll like this video. So that's basically what it does. We see the coding that I was just showing you a minute ago. And what it does is it keeps repeating this cycle going from color to color. Red, yellow, green, blue. So based on the combination of what colors are being put into it, RGB, it's going to change for those different colors. So I have it, there's a large yellow component in the background, so it's kind of offsetting the colors a little bit. But anyway, I just wanted to get you to be seeing how those colors are changing over time based on what we programmed here. So we go from 0 to 255. And so this is a quantized value going up steps, 0, 1, 2, 3, 4, all the way up to 255. And it happens for each one of these things. The red, and so here we're incrementing the green is set high. Here the blue is set high. Anyway, so those are just a couple of points that I wanted to point out there. Any comments or questions on that? Are you guys tracking with what I'm showing you? Give me a thumbs up if you're tracking what we're seeing happening here. Okay. So I'd recommend that everybody open up the Arduino IDE, even if you don't have your kit. Let's go ahead and open this up, and I want you to just create a new script. So I've done things before, so when you open it, it opens the last script that you had. And so why doesn't everybody give me a thumbs up if you have this up and running? And if you don't, I'll give you the steps on how to download and start this IDE. It works on a Mac or a PC. So anybody have that, or you want me to show you where to find it in Canvas, the link? Okay, here's the link in Canvas for the Arduino. So I'll put it in the chat as well. And so the current version is 2.3.3. You can get it on Windows, you can have it on Linux, you can have a Mac OS, both for Apple Silicon or Intel. So pick whatever one is the one that you need. So if you haven't already, go ahead and download that and open it up. And it should open up with this, but what I would want you to get is you're going to have a script that's going to start out with this. It's going to have a setup section and a loop. And those are the things that we're going to be programming with the three sub Arduino projects that we'll be doing. Did people get that? People get that running? Okay, well, I think that's a good breaking point for now. So we'll look forward to talk about this a little bit more next week. So God bless you all. I hope you have a wonderful rest of your day, unless there's any other questions that people have. All right. Thank you. Take care, everybody.